Now see, next topic, the vector equation of plane passing through the point A of A bar and parallel to the two non-zero vector B bar and C bar. In first part we see the vector equation of plane passing through the point A of A bar and perpendicular to the vector N bar. Here instead of perpendicular vector, two parallel vector to the plane are given. So from their cross product, we find a vector perpendicular to them. That means we find from this vector B and vector C, vector perpendicular to both B bar and C bar. That means perpendicular to plane. So see the theorem, theorem 10. The vector equation of the plane passing through the point A of A bar and parallel to the non-zero vectors B bar and C bar is R bar dot B bar cross C bar is equal to A bar dot B bar cross C bar. This is similar with R bar dot N bar is equal to A bar dot N bar. So this vector N bar is nothing but here cross product of vector B and vector C. So we see the proof of this theorem. Now see the proof of this theorem. So here we consider a plane passing through the point A of A bar and parallel to the vector B and vector C. That means we have to find the equation of plane passing through the point A of A bar and perpendicular to the vector B bar cross C bar, because B bar cross C bar is normal vector to this plane. So we first consider here, let the plane pass through the point A with position vector A bar with respect to origin O. Therefore, vector OA is equal to A bar. We consider another point, that is any point on that plane. So we write here, let P be any point on the plane with position vector R bar with respect to origin O. Therefore, here vector OP is equal to R bar. Now this vector B and vector C are parallel vector to this plane. So if we calculate their cross product, we get a vector which is perpendicular to both B bar and C bar. That means perpendicular to this plane, and this vector AP. Therefore, vector AP lie on the plane. So we first find the value of vector AP, that is equals to, so from this we write AO plus OP. This vector AP equals to vector AO plus vector OP. This vector AO can be written as minus vector OA plus vector OP. Now this vector OA is A bar, so we write here minus A bar. This vector OP is R bar, so we write R bar, that is R bar minus A bar. This is vector AP. Now this vector AP lie on the plane, and this plane is perpendicular to this vector B cross C. So we write here, therefore vector AP dot B bar cross C bar is So we write some note from this form. This R bar dot B bar cross C bar and this A bar dot B bar cross C bar is scalar triple product. So we write this as in box product form R bar B bar C bar is equal to A bar B bar C bar. Now we find the parametric form for the equation of plane passing through the point A of A bar and parallel to the vector B bar and C bar. So for that we consider here this point P with position vector R bar and given plane passing through the point A of A bar. So we consider here 2 points on vector AB with position vector B bar. We consider point M. On vector AC we consider point M with. Now we consider this point M and L such that they form a parallelogram. That means parallelogram ALPM is formed. So we use here parallelogram law. If we join this AP, so we write this AL and this AM as adjacent side. So we write this vector AP is equals to vector AL plus vector AM. So we denote this as equation number 1. Now this vector AL lie on vector AB which is vector B bar. So this vector AL and vector B bar are collinear. So there exists a scalar lambda such that we write this AL vector AL is equals to, we suppose consider scalar as lambda. So AL equals to lambda into B bar because AL and this AB lie on the same line. So this vector AL and vector AB are collinear. So there exists scalar lambda such that vector AL equals to lambda into B bar. Similarly, we consider point M on this vector AC. So this vector AM and this vector AC lie on same line. Therefore, there exists a scalar mu such that vector AM is equal to mu into C bar because this vector AC as vector C. So we write from this and substitute this in equation number 1. Therefore we get vector AP is equals to lambda into B bar plus mu into C bar. Now position vector. Now say next topic, the vector equation of a plane passing through the 3 non-collinear points. These 3 points are non-collinear points. So we see theorem based on this. Theorem 11. The vector equation of the plane passing through the 3 non-collinear points A of A bar, B of B bar, C of C bar is R bar dot vector AB cross vector AC equals to A bar dot vector AB cross vector BC. So here we consider point A, point B, point C. These 3 points are non-collinear points. We consider one more point, that is any point. So we consider this vector AC, vector AP, vector AB. Now when we consider these 4 points are coplanar. So these 3 vectors are also coplanar. Vector AC, vector AB and vector AC. These 3 vectors are also coplanar, and we know that when 3 vectors are coplanar, their scalar triple product is 0. So we consider here in proof, let A of A bar, B of B bar, C of C bar and P of R bar be the position vector with respect to origin O. Now these 3 points A, B, C are non-collinear points. Capital A, capital B, capital C are non-collinear. Therefore, points A, B, C are coplanar. Therefore, points capital A, capital B, capital C, capital P are coplanar. Therefore, the vector, we consider here one point fixed. So we write here the vector AP, vector AB, vector AC are coplanar.